Hey everybody, Jake here, coming at you with some more math. Today we got related rates cone problem, where the water is filling into the cone and leaking out of the cone at the same time. So here's the problem we're going to be doing. I'm going to go, step by step through this with you, show you how to solve a problem like this. Before I get into that though, I do want to point out, we're going to go through the same process that I go through with all related rates problems. So these steps that I'm going to go through, you can apply these same 4 steps for any related rates problem that you have, and it'll help you get through that problem and get to the correct answer. Before we jump into this though, I would really appreciate it if you could like the video if it does help you in the end. Subscribe to my channel. I'm going to be having plenty more math videos coming out, so definitely helps me out if you do subscribe, so you can be sure to check back in when I have more content for you. So here's the problem. Water is leaking out of an inverted conical tank at a rate of 10,000 cubic centimeters per minute. At the same time, water is being pumped into the tank at a constant rate. The tank has a height of 6 meters and the diameter at the top is 4 meters. If the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, find the rate at which the water is being pumped into the tank. Like I said, these are the steps that I would recommend applying to any related rates problem. They're going to work for all of them. The first is going to be to draw a sketch of what we're dealing with. So we need to take all of this information that we're given and put it into a picture. Just needs to be a rough sketch. It doesn't need to be, don't need a Picasso or anything like that. Just any sort of rough sketch of what we're going to be dealing with. So first of all, we know we have a cone-shaped tank. It's at a conical tank. That just means it's in the shape of a cone. So we're going to have something like this. So we got our cone shape there. We know that we're going to have water going into this cone, and we're going to have our water filled up to a certain point inside this cone. And as the water's going out, as the water's going in, there's also water going out the bottom of the cone. However, we do know that it's filling up, so it's moving, this surface right here, the surface of the water in the cone, is moving up. So first of all, let's put in the dimensions of this cone. So we know that our cone it said it had a diameter at the top, which was 4 meters. So we know that distance there is 4 meters. It also gave us a height of this cone. So we know our cone is 6 meters tall. Some other information it gave us, at the moment that we are looking at, we know that our water is 2 meters tall. So of course this is going up, it's moving upward. However, at the very moment that it's asking us to measure, we know that it's 2 meters tall or 2 meters deep. We know that this we know that this water level is rising at this very moment at a rate of 20 centimeters per minute. That pretty much covers it. So what we're trying to figure out here, it asks us at what rate is water being pumped into this conical tank. The volume of water going in here is what we are looking for. So that's kind of our key right here is that. There's one other thing that we do know, which is water is leaking out at a rate of 10,000 centimeters cubed per minute. So before I go any further, I do want to point out one thing. We're not going to deal with it quite yet, but I just want you to be aware of it because we are going to have to come back to this later. Notice the units of everything that we were given. This measurement here, here, and here are all given in meters, and this one are given in centimeters. So because everything is not in the same units, later on we're going to need everything to be in the same units. So what we're going to have to do is either convert everything to centimeters or everything to meters, so that we can kind of figure out exactly what this volume is here. If we leave everything as it is, leave this as 10,000, 20, 2, 6, 4, and just kind of ignore those units, things aren't going to end up working out properly. So that's something that we're going to deal with later. I won't get into that quite yet, but do keep that in mind because we are going to need to be aware of that toward the end. So now that we've got our sketch, this is going to be helpful for us to refer back to. What we want to do after we've done this, and this is really just to kind of get a visualization of what information we know, what information we are trying to figure out, and just kind of what's going on. And the reason why it's helpful to have a visualization of all that stuff is what we need to do now is come up with an equation which we are going to do implicit differentiation on in order to get to help us find this value. So that's the second step. Second of the 4 steps for any related rates problem is to come up with our equation. So one important thing that I want to point out about our equation that we're going to come up with, it should not have any rates of change in it. It should only have variables that represent distances, volumes, any kind of measurement of some kind is fine to have, but we don't want to have anything in our equation that represents how fast those measurements are changing. That is going to come into play later on. For now, we just need to include like heights, widths, radius, diameters, volumes, any of that kind of stuff is okay. So what we want to think about in order to come up with our equation is, first of all, what are we looking for? What is this question asking us to find? Because that is going to dictate, specifically what piece of information we need to make sure to have in our equation. So what we're looking for is how fast water is being pumped into this conical tank. Where that's going to come into play is into the volume of this small cone here. As water gets pumped into this tank, this small cone is going to be increasing in volume, right? The volume of water that's being put into this tank is going to go down to the bottom of the cone, obviously. And when that happens, the volume of this small cone here is going to increase. So if we can figure out the rate at which the volume of this cone is changing, we can use that to figure out the rate that water is being put in, because the rate water is being put in is going to directly impact the rate of change of the volume of this small cone. So essentially, what that means is we're going to have some sort of equation having to do with the volume of this cone. And once we take its rate of change, that will get us to what we're eventually trying to find. But what we're looking for is the rate of change of the volume of our small cone with respect to time. So how quickly this volume is increasing. This is what we're looking for. If we can find this, we can use that to find this information here in combination with the rate that it's draining out. So this is what we're looking for. But remember, I said our equation can't have rates of change in it. This is a rate of change, the rate at which volume is changing with respect to time. What we're going to have to do is implicitly differentiate our equation. So what you want to think about is what variable or what letter would we want to put in our equation so that when we implicitly differentiate it, or when we take the derivative of that equation, it's going to get us to dv dt, and that would just be v. If our equation has a v in it, once we take the derivative of this whole equation with respect to time, that's going to introduce a dv dt, which we can then use to find this volume. So we need our equation to have a v in it. So now that we know that our equation needs to have v, which is the volume of this small cone, we want to think about what other information we already have, what information we are given. So this is going to take into account essentially all the information that we know relating to the volume of this small cone. So let's take a second to think about the information we were given. We know at the moment that we're looking at, we know the height of this small cone. We know it's 2 meters. We know the rate of change of the height, right? We know that this water level is increasing at 20 centimeters per minute. So we know how quickly the height of this cone is increasing. We don't know the radius or diameter of the small cone, but we do know the diameter of the large cone. which, since we know the height and the diameter of the large cone, we can use similar triangles to find basically what the radius or diameter of this cone would be, along with basically this small triangle here is going to, we could use that similar triangles with this large triangle here to find out what that radius and diameter are. Because we know that this red triangle, which is the large cone, and this green triangle, which is the small cone, we know that their angles are going to be the same, so they're going to be similar triangles. Therefore, we can use the information we have about the diameter and the height of the large triangle along with the height of the small triangle to figure out the diameter of that. So we do know information about the diameter, which we can use to find radius. We know the height, we know the rate of change of the height. So we know essentially just those two things, diameter or radius and height of the small cone. So we know about the height, the radius, the rate of change of the height, which will come into play, but like I said, our equation is not going to have any rates of change in it. So we don't want to put dh dt, the rate of change of the height, into our equation. But it is okay to use h, because once we implicitly differentiate our equation or take the derivative of our equation, taking the derivative of h is going to give us something with dh dt in it. So that means h is a good thing to have in our equation. One thing to note, though, is we don't know dr dt. So r is going to be tough to have in our equation, but we do know some information about it. So it's okay to come up with our equation with r in it, because we do have some information. But we'll have to make a couple adjustments before we actually take the derivative. But anyways, the point is we know we have to have a v in our equation, and we know that we will be able to deal with having an h and an r in our equation. So height and radius of a cone and the volume of a cone. How are all three of those things related? A good place to start would be just kind of the generic formula for the volume of a cone. So what is that equation? So this is the equation that relates the volume of a cone with its radius and its height. This is just pi, that's just a constant. So this 1/3 pi is just some constant number value that we would multiply by the radius squared times the height, and that would give us the volume of a cone. So this is perfect because it does have that volume that we absolutely need in our equation, because that'll get us to dv dt. It also has r, which we know how to deal with, and h, which we know how to deal with. But like I said, we don't know any information about the rate of change of the radius. So when we take the derivative of this whole equation, there's going to be a dr dt in there somewhere, and we aren't going to know how to deal with it because we don't know the rate of change of the radius. So we have a couple options. We could either try and figure out what the rate of change of radius is with respect to time by using the information that we do know, or we can convert this equation into something that doesn't have an r in it at all, which that is probably going to be easier to do. And the reason for that is we can write r in terms of h, because we do know dh dt. So if we get some dh dt's in our equation, we will actually know how to deal with those. So that is the way that I would recommend doing this. And remember, this all just goes back to the fact that we know how to deal with dh dt. We don't know how to deal with dr dt, just based on the information we were given in the problem. If they gave us information about how quickly the radius of this cone is changing instead of how quickly the height is changing, then we would want to convert it into radius so that we would have dr dt instead of dh dt, and then we would know how to deal with it. So what we want to think about is going back to these similar triangles. We can actually figure out what r is in terms of h so that we can get an equation that's easier to deal with for us. So let's think about this green triangle here and this red triangle here. And I'll just kind of draw them off to the side here. If we have our large triangle, and then inside of that we have this small triangle, we know that these are going to be similar triangles because this bottom angle is going to be the same for both triangles because they share the exact same sides right here. And then since this is parallel to this, we know that this angle will match with this angle and this angle will match with this angle. In fact, these two angles are going to be the same because it's a cone. But the important thing is that they have corresponding angles to each other. So as a result, we know that they're similar triangles. And because of that, we know that the height of this small triangle here is 2 meters, and the height of this large triangle is 6 meters. We basically, what that tells us is the ratio between the small triangle and the big triangle, it's just 3 times its size. So therefore, since these two sides have that 3-to-1 ratio, we know that this side and this side are also going to have that 3-to-1 ratio. So this side times 3 should give us that side. So in other words, we can say 3 times this side will give us that side. So knowing that this is the case, we can solve this for x by dividing both sides by 3. So if x is 4/3, we know this side here will be 4/3. Now what we want to think about is this ratio between the diameter, right? This side just represents the diameter of this small cone, and this side just represents the height of this small cone. We know the ratio between the diameter and the height. That's what we want to figure out. It's going to maintain that same ratio as the water fills up here because these two cones share this angle down here, and we know that these angles here are always going to correspond with each other, no matter how full the water is. So this ratio between the diameter and the height is going to be maintained as the water fills up. So what we can do is set up that ratio kind of as its own ratio. So essentially, when the diameter is 4/3, the height is 2. What we want to think about is basically what we multiply the diameter by to get to the height. So if we have our diameter, 4/3, we multiply it by some number. We'll call it y, and that'll give us our height of 2. So that tells us if we multiply this by 3/4, that'll give us y equals 3/2, right? That'll cancel with that, making that a 2, 3/2. So if we multiply our diameter by 3/2, that gives us our height. So if we multiply our diameter by 3/2, that'll give us our height. Okay? So that'll be the case, like I said, no matter how full this water is. Diameter times 3/2 gives us the height. Now what we need to do is figure out an equation for r in terms of h. Well, diameter, remember, with any cone, the diameter is just 2 times the radius. So instead of having this d here, we can replace d with 2r, right? 2 times the radius gives us the diameter. And then if we multiply that by 3/2, that should give us h. Then if we simplify this, that 2 will cancel with that. We get 3r equals h. But remember, we want to solve for r so that we can plug this in for our r here. So we want to divide both sides by 3. So r equals 1/3 h. Okay? So now if we take this 1/3 h, we can plug it in for r to get a better equation. So doing that gives us the volume being 1/3 times pi times 1/3 h squared times h, right? All we did was replace our r with 1/3 h, which we just figured out those two are going to be equivalent for this cone specifically. Now we can just simplify this a bit, so that'll give us volume equals 1/3 times pi. 1/3 squared would be 1/9. H squared times h. And then we can combine our like terms. So 1/3 times 1/9 would be 1/27. Keep our pi there. And then h squared times h will be h cubed. So this will be our equation. V equals 1/27 pi h cubed. So that's it. This is the ideal equation that we want to use based on the information we have. When we take the derivative of this whole equation with respect to time, which we'll do in the next step, that'll be our third step. When we do that, this v is going to give us some sort of dv dt that we're going to be able to deal with in order to get to this answer. And the only other letter or variable in here is h, which when we take the derivative with respect to time is going to give us some sort of dh dt, which we know it's 20 centimeters per minute. So we're going to be able to deal with that as well. And there's no other variables that we won't know how to deal with. So let's take this equation and go on to the third step, which will be the implicit differentiation step. So now our third step is implicit differentiation. So all that is going to be taking the derivative with respect to time of the equation that we just found in the second step. So this is our equation that we found. All we have to do now is take the derivative of this equation with respect to time. So we're just going to do derivative with respect to time of this whole thing. So the derivative of v with respect to time is just going to give us dv dt, right? That's just because volume of this cone is some variable. It's changing as time goes on. But we're not taking the derivative with respect to v. So the derivative of v won't just be 1 because we're taking the derivative with respect to time. This little indicator here tells us that. So the derivative of volume is just simply the derivative of volume with respect to time. That's basically what this notation means in words, basically. So now we have the derivative of this over here. So again, we're taking the derivative with respect to time. 1/27 times pi is just some constant. And then we have that constant times this variable to a power. So we can essentially just use power rule here to get things started. However, we're going to have to use chain rule because we're taking the derivative of h with respect to time. So therefore, you want to treat h like a function of time, and taking the derivative of h means that you have to do the chain rule because h is another function that's being plugged into, all this 1/27 pi times itself to the third power. So we're going to have to do power rule and chain rule. So chain rule says take the derivative of the outside function, leave the inside alone. So our inside in this case is just h. Our outside is all this other stuff. So take the derivative of the outside, leave the inside alone. So our h is just going to stay as an h, but we're going to do the power rule with all this stuff here and here. So power rule says bring the power down in front. So we're going to get 3/27 times pi. And then we're going to leave the inside alone. So leave our h alone and then lower the power by 1. So that's our power rule, derivative of the outside portion. Then we're going to multiply that by the derivative of the inside. So the derivative, our inside is just h. The derivative of h with respect to time is just going to give us dh dt. So that's it. This is chain rule. We took the derivative of the outside, left our inside the same, and then multiplied by the derivative of the inside, which is the dh dt. Okay, so now we can just simplify this a little bit. There's not really a whole lot we can do, but 3/27 will simplify. So dv dt equals 1 over 9 pi h squared times dh dt. So that's about as simplified as it's going to get. So this is almost to the end of our problem. Once we've done the implicit differentiation, really the only thing we need to do now is plug all the values in that we know and figure out how that relates to the problem. So let's go ahead and do that. We know dv dt, which is the thing that we were looking for, remember? So we're not going to know that one yet. That's our goal. But so the 1/9 pi is just 1/9 pi. There's nothing really to do there. Then we need to plug in the h. So h is the height of our small cone, the height of our water. We were given the height of the water to be 2 meters. So we know that that would be 2 meters. So this is where the units is going to come into play. We either need to convert everything to centimeters or we need to convert everything to meters. Centimeters is probably going to be more accurate just because having it in that smaller unit is going to give you a more accurate number. So we'll go with that. So 2 meters is the same as 200 centimeters. So our h is going to be 200. And then we're going to square that and then multiply by dh dt. dh dt is the rate of change of the height. So how quickly our water level is rising, which is 20 centimeters per minute. So then we're going to multiply that by 20. So then if we multiply this all out, 200 squared times 20 times 1/9 pi would give us about 279,252.68. So basically, the volume of this cone is changing or increasing at a rate of 279,252.68 cubic centimeters per minute. So we know that the volume of this water is increasing at that rate. However, that's not what the problem asked us for, remember. The problem asked us to find how quickly water is being pumped in. We know that the amount of water that's in there at any moment is changing at this rate, but water is going in at the same time as water is coming out. So in order for the volume of this water to increase at this rate, it needs to be pumped in 279,000 cubic centimeters per minute faster than it's draining out. So essentially the rate that it's pumping in will actually have to be this plus 10,000 centimeters cubed per minute. So basically the rate in has to be the rate of change of the volume that's in there plus the rate that it's going out. So it's going in, here's how quickly the volume's changing, here's how quickly it's draining out. It must pump in, at essentially 279, 252.68 plus this 10,000 cubic centimeters per minute. So that'll give us about 289,252 and 0.68 cubic centimeters per minute. Decimals kind of look like commas there. So that's it. That's how quickly water is being pumped in. So that's really it. Like I said, every related rates problem is going to follow these same 4 steps. First, you want to draw it. Just draw a sketch of what you're dealing with. Like I said, it doesn't need to be a great picture. You just need some sort of sketch so that you can see what geometric shapes you're dealing with, and so you can sort out what information you're looking for and what information you already know. Once you've drawn your picture, you'll use that, specifically the geometric shape, to come up with your equation. Coming up with your equation should probably involve some sort of volume or surface area equation for some sort of shape, like it did here, the volume of a cone. And you're also going to want to sort through what information, what variable you have to have in there, and then what other variables it's okay to have in there. And then, like we figured out with the radius, what variables we want to figure out how to rewrite in a way that we actually have some information. So we had to figure out R in terms of H because we knew H, we knew dH dt, but we didn't know dr dt. So we had to kind of rewrite it in a way that we had some information about it. Then once you come up with your equation, you take the derivative of the whole thing, both sides of the equation, or in other words, you need to implicitly differentiate or do implicit differentiation to take the derivative of both sides with respect to time. That's your third step. Once you've done that, then you just need to solve for the rate of change that you're looking for. That's the fourth step. So solving for that desired rate of change just means getting the letters, the rate of change that you're being asked to find by itself, and then plug in all the other values that you know that you were given, and that'll leave you with the rate of change that it's asking about. In this case, we had that one extra step of converting it to figure out how quickly water was actually being pumped in, because our equation wasn't really asking us the rate of change of this volume. It was asking us how quickly water is being pumped in, because there was also some water leaking out. So there was kind of a little extra here, but that's just, thinking about the wording of the problem. So those four steps, apply them to any related rates problem. It's pretty much the same idea for all of them. Hopefully that helped clear things up for you. If you have any questions that I didn't address in the video, drop them in the comments below. I'd love to be able to address those for you and help you get through these related rates problems, because I know they can be challenging. It's a tough topic to learn, and obviously these problems take a long time, so it's hard. So yeah, if you have questions, let me know. I'd love to hear them. If you want to go check out, I have a page on my website where I go through this problem in writing. If you prefer to see it in writing, I'll put a link in the description below, so go check that out. If the video was helpful for you, please give it a like and subscribe. Come back. I'll be posting plenty more math videos. So subscribe, hit that little bell icon so you can be notified when I post something new, and I hope to see you back soon.